Hi everyone. In the last lecture, we looked at the Schmidt trigger, the problem with Schmidt trigger circuits that operate on a single supply voltage. What we said was that the low to high threshold voltage in both non-inverting and inverting Schmidt triggers were stuck at 0 volts. Okay, and this is what these two were the plots for the inverting and non the this one here is an inverting Schmidt trigger, this one here is a non-inverting Schmidt trigger, and these were the transfer characteristics of the inverting and non-inverting Schmidt triggers. Okay, and we can clearly see here the low to high threshold voltage in both these cases is stuck at 0 volts. How do we fix this? So usually bear in mind that in any single supply system, we would also assume that your input signal is more or less unipolar in nature, meaning it will also go from a minimum of 0 volts to some maximum value. It will keep oscillating between some minimum and maximum value, okay, which is always greater than 0. That's the assumption under which we will operate, which means both the threshold voltages, whether it's low to high or high to low threshold voltages, should be greater than 0. How do we do that? Since we have already discussed Schmidt triggers with symmetric threshold voltages, we said, if you recall our discussion or lecture on realizing Schmidt triggers with asymmetric threshold voltages, we said by adding an offset voltage, I can move this entire transfer characteristics to left or to right. Okay, either I can move it in this direction or I can move it in this direction. So that's the idea we're going to implement here as well, and this is something you will normally see in data sheets or any practical op-amp based circuits as well. So in the first case, I'll consider the inverting Schmidt trigger. In an inverting Schmidt trigger, instead of connecting this node to ground, I'm just connecting it to VREF volts. I'll not go through the analysis, but if you guys recall from our previous discussions, I wrote the low to high threshold voltage, the point where the low to high threshold transition takes place, happens at instead of it happening at minus beta Vsat, it will happen at minus beta Vsat plus 1 minus beta times Vref. Okay, it will actually be minus beta Vsat here, but since it's a single supply system, that voltage will be 0. So what you will be left with is the low to high threshold voltage will simply be 1 minus beta times Vref. If you guys don't recall all that, just you can take this characteristic, you can just take this characteristics here and add 1 minus beta times Vref to both these voltages. Just add 1 minus beta times Vref. That amounts to shifting this characteristics to the right. Right? That's what happens here. I have shifted this characteristic to the right. And if you see, the difference between the low to high and high to low threshold voltages is simply equal to beta times VDD. In case of Schmidt triggers that operate on dual supplies, the difference between the high to low and low to high threshold voltages will be 2 times beta times VDD. Okay, that's the only difference here. So now I was able to shift the characteristic. Now I have two different low to high and high to low threshold voltages. Okay, so I have two equations, two unknowns. If I give you guys the low to high and high to low threshold voltages, you will be able to design this Schmidt trigger because you have two equations and the two unknowns. The two unknowns are Vref and beta. Okay, they are two nonlinear equations. You can solve them using a computer and get the values of beta and Vref. Okay, desired to get this characteristic. What normally the circuit that you will see in literature, instead of connecting it to a voltage source Vref, we normally derive that Vref from the supply voltage itself. If you guys look at any data sheets, you will find a circuit like this very commonly, especially for Schmidt triggers that employ a single supply voltage. You will see you would be deriving this Vref using the supply voltage itself. You will see a potential divider and the output of the potential divider directly connected to this node. Okay, and this resistance is R2. So what can we do? Immediately we can just represent this by a Thevenin equivalent. The Thevenin equivalent for that will be what? A voltage source of value R4 by R4 plus R3 times VDD. That's the Thevenin equivalent. And the Thevenin resistance will be, if you short circuit this and find the resistance here, that will be R3 parallel R4. Okay, I'm simply calling this term R3 parallel R4 as R1, and this term, the potential divided, the potential divider's output, which is R4 upon R4 plus R3 times VDD as VREF. Okay, so that's it. So I have now reduced this circuit to a circuit in a form that's something that we have analyzed a few moments back. Okay, it's the same circuit. All I'm doing is just adding an offset to both these points. So I'm shifting these characteristics to the right. So both the high to low and low to high threshold voltages will be in the positive quadrant. Okay, it will be always in the, they both will be positive, they both will be greater than 0. Okay, so similarly, if I want to build a Schmidt trigger for a single supply system with a non-inverting Schmidt trigger for a single supply system, we have again seen this circuit previously as well. To the inverting terminal, I'll just have to connect VREF and a potential divided value of R1 and R2. So this amounts to shifting the whole transfer characteristics by VREF volts. So you can just take this characteristic here. Let me just show this. So take this characteristic and shift this guy by, shift this whole graph. If you shift this whole graph in this direction by VREF volts, you will get this characteristic. I mean, see, I'm not doing the mathematical analysis because I've already performed the analysis of this circuit in one of the previous lectures. You can go through that. And so the lecture is on Schmidt triggers with asymmetric threshold voltages. Okay, you can go through that lecture. I've already done that analysis. So all I'm saying is, by just connecting VREF and a resistor divider R1 and R2, it amounts to shifting this. What effect does this have on the transfer characteristic is that it amounts to shifting the entire transfer characteristic to the right by VREF volts. So the low to high threshold voltage, so this here is a non-inverting, this here is a non-inverting Schmidt trigger. The low to high threshold voltage will be VREF itself. Okay, previously it was 0, so it was VREF itself. The high to low will be VREF minus beta times VDD. Okay, so again, the difference between the high to low and low to high threshold voltages, this gap is beta times VDD. Okay, so V low to high, in this case low to high will be higher, so I have to do this. V low to high minus V high to low will be beta times VDD. Okay, so now I've realized a non-inverting and an inverting Schmidt trigger with positive threshold voltages. Both high to low and low to high will be positive threshold voltages, and this is something very commonly used in Schmidt triggers that operate on a single supply. Okay, so that's the only difference. Because I've already discussed how to analyze this circuit, I'm not going into the in-depth in analyzing the circuit. I'll leave that to you guys. I've already done that in one of the previous lectures, so I'm just quoting the final results here. By adding this reference voltage and a resistor divider R1 and R2, it amounts to shifting this whole characteristic to the right by VREF volts. Okay, we have already seen how that happens. Okay, so that's how you should do it. So in case you are given a single supply system, then you have to, the way in which you build a Schmidt trigger for a single supply system is by taking the circuit for a dual supply system and adding an offset voltage to it. Okay, that's the way you go about it. Thank you.